The main advantage of the 2's complement representation is that both addition and subtraction can be performed using the same algorithm and therefore the same circuit. In the case of an addition like x plus y, we simply provide the 2's complement values of the operands as input to the same binary adder used for unsigned integers. We perform the sum, and differently from the algorithm used for unsigned integers, we ignore the final carryout bit. When performing a subtraction like x minus y, we rely on the identity x minus y equals to x plus minus y. So the only difference is that we compute the opposite of y before using it as second operand. Since this is an operation on n bits, the result is correct if and only if it lies within the range from -2 raised to the power of n minus 1 to 2 raised to the power of n minus 1 minus 1. If the result falls outside this range, we encounter arithmetic overflow or underflow. Overflow and underflow conditions in n-bit addition and subtraction are easy to identify and occur in the following 4 cases. When adding 2 positive numbers, if the sign of the result is 1, this is a case of overflow. When adding 2 negative numbers, if the sign of the result is 0, this is a case of underflow. Alternatively, when subtracting a negative number from a positive one, if the sign of the result is 1, this is overflow. When subtracting a positive number from a negative one, if the sign of the result is 0, this is underflow. All of these scenarios are summarized at the bottom of the slide, where you can see that it's sufficient to examine just the most significant bit of each operand and of the result to detect the presence of overflow or underflow. The diagram shown here represents the architecture of an n-bit 2's complement adder subtractor. It consists of a main module, which is a generic binary adder, and some surrounding logic that handles special cases such as underflow and overflow, as we've just discussed, and the selection between performing an addition or a subtraction. If the not add or subcontrol signal is 0, the adder receives the n-bit operands x and y directly, and the carry-in input C0 is also set to 0. On the other hand, if the operation is a subtraction, then C0 equals to 1, and the bits of operand y are inverted. To this purpose, the XOR function here behaves like a controlled switch. When not add or sub signal equals to 1, the bits of y are inverted for subtraction. When not add or sub equals to 0, they remain unchanged for addition. The logic block located at the bottom left of the diagram is responsible for detecting overflow and underflow conditions. Finally, the adder subtractor block, shown as a single unit here, can be implemented internally using different architectures. For example, a ripple carry adder or a carry look-ahead adder, depending on the performance and area requirements.